US Physics Olympiad, year 2014, USAPHO. Final round. Problem A4. A positive point charge Q is located inside a neutral hollow spherical conducting shell. The shell has inner radius A and outer radius B. A is not neglectable. The shell is centered on the origin. Part A. Assume that the point charge Q is located at the origin in the very center of the shell. First question. Determine the magnitude of the electric field outside the conducting shell at x equals b. Question 2. Sketch a graph for the magnitude of the electric field along the x-axis on the answer sheet provided. Question 3. Determine the electric potential at x equals a. Question 4. Sketch a graph for the electric potential along the x-axis on the answer sheet provided. Part B. Assume that the point charge Q is now located on the x-axis at the point x equals 2a/3. Question 1. Determine the magnitude of the electric field outside the conducting shell at x equals b. Question 2. Sketch a graph for the magnitude of the electric field along the x-axis on the answer sheet provided. Question 3. Determine the electric potential at x equals a. Question 4. Sketch a graph for the electric potential along the x-axis on the answer sheet provided. Question 5. Sketch a figure showing the electric field lines, if any, inside, within and outside the conducting shell on the answer sheet provided. You should show at least 8 field lines in any distinct region that has a non-zero field. Solutions. First, let's do the picture for part A. We have charge Q in the center of this sphere, and we have a spherical shell with inner radius A and outer radius B. First question. Determine the magnitude of the electric field outside the conducting shell at x equals b. Solution. Here we can use a Gauss law, and according to this Gauss law and due to symmetry, if we have inside of a spherical region charge Q, the outside electric field will be this expression as a function of r. It means that on the distance b, just outside the shell, electric field will be this one, 1 over 4 pi epsilon 0 q over b square. That's the answer for question 1. Question 2. Sketch a graph for the magnitude of the electric field along the x-axis on the answer sheet provided. Solution. Because the shell is conductor, we have a zero electric field inside of it, because electric charge distributed on the inner shell with a charge negative Q, and there is a charge positive Q on the outside side of the shell, and both charges are uniformly distributed. It means that inside of this shell electric field is zero due to Gauss, and due to Gauss inside the shell with distance less than a, electric field is the same as outside the shell, and we can sketch the graph. And finally we have this expression for electric field for question 2, and let's sketch it. Here we have a graph for this behavior where we have two parabolas from right side and the symmetrical from left side with a 0 between negative b and negative a and the positive a and the positive b. That's the answer for question 2. Question 3. Determine the electric potential at x equal a. Solution. Because this shell is conducting, it's an equipotential surface. It means that the potential in point A equal to potential in point B. Outside of this radius greater than B, electric potential the same as potential for charge inside the sphere. So it means that this is the expression for potential in point A and B, which is equal 1 over 4 pi epsilon 0 q over b. Question 4. Sketch a graph for the electric potential along the x-axis on the answer sheet provided. Solution. So we have potential outside of this shell for x greater than b equal this one. For x between a and b, that's a constant, same as in point b. And for x less than a, that will be same as for point charge, but shifted by this constant, negative 1 over a plus 1 over b. If we sketch this, that will be like this. X greater than b, we have regular potential for point charge. Here between a and b, that's constant, and less than a, that will be shifted by constant. So that's the answer for question 4. Part B. Assume that the point charge Q is now located on the x-axis at point x equal 2a over 3. Question 1. Determine the magnitude of the electric field outside the conducting shell at x equal b. Solution. Now, because inside the shell electric field still 0, it means that we have a negative charge Q distributed on inner surface, but now it's distributed not uniformly. It's distributed exactly like the way to cancel charge in point 2a over 3, which is not symmetrical. And after that, the charge on outside surface will be distributed uniformly due to same Gauss, and we have the same answer as for part A, question 1. So that will be the answer for question 1. Electric field in point B equal 1 over 4 pi epsilon 0 q over b square. Question 2. Sketch a graph for the magnitude of the electric field along the x-axis on the answer sheet provided. Solution. So for the field outside the shell for x greater than b, we have the same result as for point charge in the center of the sphere. But inside the shell between a and b, we have 0 electric field, and for x less than a, we have more complicated situation, because it depends on the distribution of charge on the inner surface, and that is required is that it diverges at x equal 2a over 3 and is higher at x equal a than at x equal negative a. So basically one can find the field for r less than a exactly using the method of image charges. For r less than a, the shielding charges on the inner surface produce the exact same field as a single point charge would. The locator of this image charge can be found by inverting the original point charge about the circle r equal a. But this is out of the scope of this problem. So finally we can sketch the graph for this electric field. That will look like this. So we have for x greater than b, from right side and symmetrically from left side, we have the same field as for point charge in the center of the sphere. After that we have zero field between a and b from both sides, and inside the shell for x less than a we have diverging for x equal to a over 3, and kind of complicated field, but still back proportional to 1 over r square, where now r is distance to point to a over 3. So that's the solution. Question 3. Determine the electric potential at x equal a. Again we have electric potential outside the sphere for x greater than b, the same as for point charge in the center of this sphere. So that will be this expression: potential in point A the same as potential in point B, because this shell is equipotential surface. So that's the answer for question 3. Question 4. Sketch a graph for the electric potential along the x-axis on the answer sheet provided. So here we have the same situation. Outside of this shell for x greater than b we have the same potential as for the point charge, and between a and b we have constant potential, and after that we have potential back proportional to 1 over r, where r is distance to point x equal to a over 3. So that's the main idea. And the graph for this potential will look like this. That's the same as for point charge in the center of this sphere, outside b, and it's a constant between a and b, and it looks like 1 over r inside this shell for x less than a. Question 5. Sketch a figure showing the electric field lines, if any, inside, within and outside the conducting shell on the answer sheet provided. You should show at least 8 field lines in distinct region that has non-zero field. So obviously electric field will be spherically symmetrical outside the shell when r greater than b, must be 0 inside the shell between a and b, and the field lines must be terminated perpendicular to the surface of conductor. That's the picture for this electric field lines, and this is the answer for question 5.